a little bit early on Friday. If you can try to get here at as close to 11:40 as you can, we'll try to start at 11:45. Hopefully the other class will move out of our way a little bit. Yeah.
Are we not over to on Friday?
No. No, because we won't have. Well, maybe it's not due, but I'll assign it because it's gonna be on the test. But it doesn't. I mean, you got to study it, so it might as well be due because it's going to be stuff on the exam that we cover Wednesday. So, yeah, I would be happy to make it due Monday, but it doesn't really make sense. You got to work on it to study. So, it'll be due Friday. Yeah.
Written homework for next week, is it just going to be all stuff that we cover on Monday then, like after the exam?
And Wednesday. So.
Well, like, if it's due next Wednesday. So it'll be stuff that we cover this Wednesday too?
Yeah, maybe.
Okay.
Well, yeah, we'll see. I'm not sure. I'm not sure what written homework will look like. I haven't thought about it yet, but so I can't really answer that question. But it's a good question. It's a good question because it will be different than normal. Other questions? Okay, so you guys have some. Hopefully, you dug into the homework, and we're starting to get some proficiency with lines. So the next thing we want to talk about is planes. So a plane, right, is a different animal than a line, because a line is how's a line a different kind of thing than a plane? What's that? Yeah, a line is one-dimensional, right? So but even we could have like a curve in space. A curve in space would be similar to a line. So that would even be three-dimensional. So if you thought about a curve in space, just going everywhere, that's going in and out of not just in the screen, but in and out also. How is that curve different than a plane? Is that a hand? No. So what's the difference? Yeah.
It's a set of points.
Which is a set of points?
So the line is a set of points.
Okay, and the plane is not?
I would say it's a set of lines, but
yeah, it's still a set of points, right? It's still they're both a set of points. So the one-dimensional thing is still kind of on the right track, right? So like even though this is a curve in three-dimensional space, there's still a one-dimensional element to that, right? That it's like a string of points, right? A string of points. So you still, given any point, there's still only one way to go, right? Forwards or backwards, even though it's curving through three-dimensional space. Whereas on a plane, that's not true, right? If you're on the plane, really, how can you define and how many ways can you go, right? How many coordinates do we need to say how many ways you could go? 2, right? So you kind of like you can go like you think of components. You can go in a direction that would have some kind of like vertical one component and another orthogonal component, right? So a plane is an example of what we call surface. As opposed to a curve. Where a line is a type of curve, right? A line is a type of curve. Surfaces need, so with surfaces, it's kind of like you have like 2 dimensions to kind of define them, whereas a curve just needs 1 dimension. Okay, that's just the point is that they're different, right? And you can kind of visualize how they're different. So when we define a plane, so then the moral of the story is that, a line, we have our vector function, right? Oh no. That said though. Okay, so a line is a vector function. Or what are, so all points are what? A given point plus all scalar multiples of a parallel vector or direction vector of the line, right? So we know all about that. And we saw where that equation came from and how that generates every point on the line. So this is right, every point on the line. So a line is a vector function. But so because a plane is, it's not going to be a vector function like this, right? It's not going to be a vector function like this because it's a different type of set of points than a line or a curve is. Okay. So, but what's similar is that we're going to need something that gives us the orientation of this plane in space, right? Something that tells us how it's oriented, angled, slanted, if you want to, if you will, okay? And then something that tells us where it is, right? So let's talk about the orientation of the plane. What's going to determine, what kind of mathematical thing will we have that will determine how a plane is, say, oriented in space? Noah, what do you think?
Slope. Slope.
Yeah, but so like how fast water runs down or something like that? Is that kind of what you're thinking? Like how steep it is relative to z? But the problem with that is we've got all kinds of planes that have the same steepness relative to z. You see that? Like so if this is whatever, you know, a slope of 3, then I could have all these different planes that have a slope of 3, so that doesn't lock it down. So we need something that like really locks down exactly in all 3 dimensions what it is. Yeah? Okay, a vector. So how about a vector in the plane? So this vector is that vector is parallel, or we could put it in the plane. So does that vector then tell us the orientation of that plane? Why not? Why doesn't a vector in the plane give us the orientation of the plane? Meaning how it's angled in space or how it's slanted in space.
You really just kind of move it along the plane.
What's that?
You could really just kind of move it along the plane. You could like translate it, or you could spin it around. And it's a different angle, but it's still on the plane.
So what is it about that one vector that doesn't give us a unique plane? It's really, yeah, you're kind of on the right track. Right. So you see that if that vector was like an axis, that you'd have an infinite number of planes that would contain that vector, right? You can imagine it spinning around, right? Spinning around like this, right? So a vector in the plane is not going to give us this orientation, okay? What's that? 2 vectors would, okay? Is there one vector that gives us orientation of the plane? Would an orthogonal vector do it? Too far, I just want this one right there. There we go. Would an orthogonal vector lock down the orientation of the plane? Yeah, so really, so now there's, can you imagine all planes that are orthogonal to that vector? All planes that are orthogonal to that vector. Do they all have the same orientation or kind of angle in space? Yeah, they would, right? So you can imagine a bunch of parallel planes to that. They'd all be parallel, so they'd all have the same normal vector. So when we say normal is another word for orthogonal. So this will be a common thing we use. Normal is somewhat synonymous with orthogonal. So like, for instance, with planes, you call that orthogonal vector to the plane, you call it the normal vector. Okay, so this is the normal vector. Why? Because it's orthogonal to the plane. All right, so then what else do we need? So we've got the inclination of it in space, right? So we know that any plane that's orthogonal to that is going to have the same kind of inclination or kind of angle or orientation in space. So then what else would we need? If we had one point on the plane, then do you see that the combination of the one point on the plane and this normal vector would lock down exactly what plane we would have? Does that? Oh, I see some nods. Okay. So that's right. So if we have a point and we have the normal vector, those are kind of the 2 basic things that could generate a specific plane that we want to define. So in terms of the point, so for instance, so I'm showing the point that we know right there, and I'm putting the normal vector. We could put the normal vector with its tail at any point on the plane, but I'm putting it with its tail on our known point. Okay, so that's our known point, and so we'll call that x naught, y naught, so p naught. So our known point, p naught, is x naught, y naught, z naught. And I'm showing it as a, what? As a position vector. X naught, y naught, z naught. Okay, well then there's, so what we're after is to representing, if by saying we're defining a plane, what we're saying is we're going to represent all points in the plane, right? All points. Ahead of myself here. Okay, so this red vector then, the red one, that point right there is just any arbitrary point in the plane. So x, y, z. So its position vector is x, y, z. What's that? That's all points in the plane, okay? All points in the plane. So we've got our known point, and we've got our normal vector, and then we've got this vector that represents all points in the plane. So for instance, I can still work. So this is gonna, so we want some kind of equation that's gonna give us every point in the plane, okay? So the way we're going to do this is we're going to look at, can you tell me what, a lot of colors here. Can you tell me what vector this is right here? From this point, I'm supposed to be from this point. If I turn over. Okay, so what vector is from this point to this point? Can you write an expression for that vector? Yeah, is it Harris? Okay, Harris, what do you think that vector is?
We'll just do the XYZ vector minus the X naught, Y naught, Z naught.
He wants x, y, z minus x naught, y naught, z naught. That is, if you were thinking that, you're correct. That's right. So that vector is x, y, z minus x naught, y naught, z naught. And tell me about that vector. What's true about that vector? This is lies on the plane. Okay, right. Two things. So to say it lies on the plane, we know that vectors are normal. So more generally, that vector is. We could put it in the plane, but no matter where it is, it's always parallel to the plane, right? Yes, and we do. So we think about it in the plane, but generally, because vectors are mobile, it's parallel to the plane. And then Lauren said something else. Since it's parallel to the plane or in the plane, it's orthogonal to this vector, our normal vector. So our normal vector is ABC. So that, the fact that this vector here is orthogonal to our normal vector is what allows us to set up the equation. So what would we write to set up the equation of a plane if we know that every vector in the plane, right, every vector parallel to the plane has to be orthogonal to the normal vector. So that frames how we set up the equation. Anybody? He said dot product equal to 0. That's it. Yeah, so we're going to take this vector right here and take the dot product with this one, and that has to equal 0. And that's going to define every point, these red points, x, y, z, that are on the plane. Okay, so we're going to do dot product equals 0. Can we subtract these out here? So what is it? It's going to be x minus x naught times y minus y naught. Or sorry, comma. Okay. Dot ABC equals so that that gets us going, and then we're going to actually do the dot product. So what do we get? A times x minus x naught plus, this is the easy part, right? Let's do the dot product. Equals. So, is it a vector function? Yeah, so now what is this? So what would be, if we have a particular plane, what would be variable and what would be actual value? So A, variable or value? No. Fight it out. You guys are split. It's a value because it's the normal vector is known, right? That ABC will be known. What about X? Y? Z. That's your X, Y, Z. That's your every ordered triple that lies on the plane. X naught, Y naught, Z naught. That's known, right? So that's known. So what is this? This is not a vector equation or a vector function, but it's just an equation of X, Y, and Z. So for our purposes now, lines and curves in space are a vector function. By picking different values of this parameter, we get different points. But a surface is a whole different beast, right? A surface is an equation of X, Y, and Z. It's not, so like all the, kind of the vector stuff is gone, right? So it's every ordered triple X, Y, and Z that makes this equation true. So this is how, if you're given the point and the normal vector, this is how you'll set up your equation. But you'll also see equations of planes given in a different form. So we could multiply these out and then move all the constant values over. So we'd have AX plus BY plus CZ would equal what? AX naught plus BY naught plus CZ naught over here, right? So we can just, that's all just a number. So we just call D. So D is, just know that it equals, where does it come from? AX naught plus BY naught plus CZ naught. So do two different equations of a plane. This is the one you use to, if you're told to write a plane. Here's some information, find the equation. This is the one you'll use, right? Because you'll need to get a point, and you'll need to get the normal vector, and then you just plug it into this. Now often, if you're given a problem, they say, here's a plane, such and such, it'll often be given in this form. So in this form, what do you know right off the bat by looking at it? What do you know about the plane if you're given a plane in this form? You know the normal vector, right? You just pull off the coefficients, and you got the normal vector. But what you don't know, right, by just glancing at it is point. Could you generate points? Would you be able to generate points? How would you be able to start generating some ordered triples? What would you do? Say, I just want to start getting some points. Yeah.
Put in values for X and Y and solve for Z.
Right. So there's going to be, yeah. So you just pick any two variables and give them values, and that will determine the third variable. And then you'll have an order triple that makes that thing true. And you just want to get as many order triples as you can that make it true, if that's what your goal is. Okay. All right, so questions on how we develop the equation of a plane, right? So we got the known point and every point. So again, this is now every point. So if you the red one then is every point X, Y, and Z that will satisfy the equation we came up with. AX plus BY plus CZ equals D. And that came from this difference of these two, the all points and the one we know, has to be orthogonal to the normal vector because it lies in the plane. So we did the dot product equals 0, and we did the math, and we got these two equations. So if you're told to write the equation of plane, you're going to be setting it up this way. And you could easily change it into this. When you're given planes, you're often given planes this way. You might be given it this way, but you're often given it this way. AX plus BY, C equals D. Any questions? Okay, so the rest of the time, I have practice problems for you. Starting easy, getting harder. Last chance, can I erase? Okay. And we'll do, so I'll let you work on it for a while, and then we'll work through as much as we have time for. I doubt we'll get through all this, but again, this is going to progressively get more and more challenging, okay? So hopefully we'll get halfway through. So plane 1, P1, has normal vector 2, negative 2, 1, contains point 1, negative 1, 0. And then from that, you're going to start writing some planes and lines. Okay, so lines are involved here. So whenever you're doing stuff with planes, you can get lines involved too. So this is a good review of that stuff. Work together. Okay, let me just talk through some, and then I want to kind of do a little bit of number 5, okay? So, everyone good on number 2? So this picture should kind of get what you need, right? To write the equation of a line, you need the parallel vector or direction vector of the line, and you need a point on the line, any point. Some of you are saying you need the initial point. There's no initial point of a line. There's no such thing as an initial point of a line. It's just a set of points, okay? So you need any point on the line, and then you need a direction vector. So I guess you could call it that, but there is no the initial point, right? Anyway, so so everyone clear on number 2? How you're going to get the direction vector, how you're going to get the direction vector of the line, and a point on the line. Are we good? Okay, number 3. So what do we need to write the equation of a plane? We need a point. Any point on either of these lines will do, right? Every point on either of these lines can be a point in your plane. And what else do we need? The normal vector, right? The normal vector, which we can get by? Yeah, so it needs to be, the normal vector will be orthogonal to both direction vectors of the lines, right? It'll be orthogonal to the red direction vector and the blue direction vector, which means use cross product. So the cross product will get you the normal vector to that plane. Then pick any point on L1 or any point on L2, okay? And then you can write it. Okay. Containing L2 and the point 1, 3, negative 2. I think I want to go to number 5 for time's sake. So that's kind of a moderate problem. You should be able to do that with a little gray matter. You should be able to figure that out. Okay, number 5. Line of intersection of 2 planes. Let's see if I can make a good drawing here. Doubtful on the first try. I want you to think these 2 planes are close. Let's do this. There we go. So the dotted line is what we're after. I'll have to do that. Okay. So the dotted line is what we're after. And so what do we need? We need a point, any point on the line. And what's going to be true about any point that you pick relative to the planes? So what about that point relative to the first plane? It's on the plane, right? What about this? It's on both planes, right? Every point on this line of intersection is on both planes. Okay? The planes extend in all directions, right? The planes extend infinitely in all directions, right? So this point is going to be on both planes. All right, so then the question is, how do we get the direction vector of the line? Some of you can see it. How can we get the direction vector of the line? Someone who figured it out. Yeah. Is it? So is it orthogonal to, let me draw the first normal vector here. So this is the blue B, plane B, say. Blue. Here's the orthogonal vector for the blue plane. Is that, since it's normal to the plane and this direction vector is parallel to the plane, are they orthogonal? Yes. And then here's the red plane. This one here is red. And so that's a normal vector of the red plane. Is our direction vector of the line normal to that? Yeah, because this direction vector is parallel to both of these planes. So it's going to be normal to both of the normal vectors of the planes. So this is like that. And then this is like that. So do you have a roadmap to do this? So to get the direction vector of the line of intersection of planes, it's going to be cross product of the two normal vectors of the two planes. Now, what about getting a point? It's got to be a point on both planes. So you're able to get a point on both planes. Anyone can explain the strategy for that? What's that? Solve for a variable? So what are the two? I don't have time. But yeah, it's basically you have degrees of freedom here. You can like plug in an x into both. Let's see. Plug in x into both, and then you have two equations of y and z, right? So you could just say x equals 0 for both planes, and what you'll be left with is two equations of y and z, two equations, two variables. So when you solve for those equations simultaneously for y and z, you'll get the y and z coordinates of the point that lies on both planes. Does that make sense? So there's a one degree of freedom there. You have two equations and three variables. Pick a value for one of your variables, solve out the other two, and that's an order. And remember what you're trying to do. You're trying to find an ordered triple that satisfies both your plane equations. So check your work. You get an answer. It should make the first plane equation work, and it should make the second plane equation work, since it's on both planes. Okay.